All right, guys. So today I want to be talking about how to visualize attention heads. So typically in these sort of transformer models, and let's just kind of, I have a bunch of other videos about transformers already, but sort of a high level idea, right? So typically when you're building some sort of like language model, right? So the goal in any language model is you have like a sequence of tokens, like let's say x1 to xn, where the something could be like I am Mark, so this would be x1, this would be x2, this would be x3. And so I want to translate this, right? So I want to come in and I want to say this is je suis Mark. And this would be like, let's say y1, y2, and y3. So typically the way this works is like in traditional architectures like recurrent neural networks, is that you would sort of do this like sequentially, where you would say first come up with an encoding for x1, then come up with an encoding for x2, then come up with an encoding for x3, use that compressed encoding of all of them to get something for y1, and then use that to get something for y2, and get that for something for y3. But sort of like a natural question you may have here is that, well, like in this case, I want to sort of figure out like which words should I be paying attention to, and as opposed to just paying attention to this final output here, so the final encoder output, what I actually want to be doing is paying attention to the entire sequence. So let's say in this case I want y1 to be informed by x1, x2, x3. I want y2 to be informed by y1, and then also these guys. And I want y3 to be informed by these guys. So this is a lot of arrows. But sort of like this makes the point. And so notice that like this is going left to right. You could potentially have like y3 be informed by y2, and this is sort of like goes into details that are specific to each sort of implementation of a transformer model, like whether it's BERT or GPT-3 or Albert or etc. There's a billion different ways of having attention models. And so the way they differ is basically how do you draw these connections? Like, are you looking at the like future words? Are you looking at all of them? Are you looking at all previous sequences? Are you skipping one? Are you looking at some in like a logarithmic boundary? But for all intents and purposes, this is sort of an implementation detail. But in general, the way sort of the question we're in general wondering about is how do you know if your transformer is basically learning good. Learning good is learning well. Is good. So there's a bunch of ways of doing this. Like so, typically, like let's say in BERT, there's sort of two ways. Maybe I would say three ways actually of doing this. So way number one is you look at what's called MLM accuracy. So this is called like masked language modeling. So the problem here, like what masked language modeling is you have a sentence, like let's say, je suis Marc. And then basically I'm going to come in here and I'm going to remove this and I'm going to turn it into a mask. And so the problem becomes, can I predict what this is given the surrounding context? And so my accuracy on these predictions determines the MLM accuracy. Another way of doing this, as opposed to looking at it in terms of tokens, like we can look at sentence. Like let's say the sentence is I am Mark, and then the second sentence is I am hungry. So what next sentence prediction does is you basically come in and you say, okay, well, given this sentence, here's like a list of multiple choice of a bunch of candidate sentences. Predict which one is the next sentence. For example, it could be I am Mark, I'm hungry, I am not hungry. So you basically create these sentences using others, you add these sentences based on other sentences that already exist in the data set, just not the immediate next sentence. And sort of the final way is what I would call like end level task performance. So the point here is that you don't explicitly come in and say, this is how good Bert is. What you instead do is you're like, okay, great, I trained the language model, and then I'm going to test this language model out on part of speech tagging or domain, dependency parsing. Let me just delete this. Why is this doing this? Okay, never mind. So yeah, like let's say dependency parsing, for example, or it could be something like a summarization. But the point is that all of these, like while like BERT is self-supervised, because it's basically using the data set itself to figure out how good something is. The end level performance is supervised. But there's sort of one additional thing that I personally have found very interesting lately, and I sort of came across this from the protein literature, and this is going to be the main subject of the talk today, but this is sort of like the background that you would need to understand what's going on. And that is visualizing the attention heads. So what does this mean? So typically here, like we've talked about like a single, just like one attention layer. Like let's say here in this case, as you can see here, here, like this is just like basically like one form of attention, and it's specific to a specific sentence. Because each of these will have weights, like basically each connection and attention will have a weight W. And to add to that, like it's not like we usually just have one attention matrix. Like you could have like thousands or potentially like millions of these or whatever. And so, what's a good way to visualize all of this, and what can you learn from it? So this is sort of like the main subject for today. So I mean, so let's like without further ado, I think we're in good shape to sort of get started at this point. Obviously, if you have any questions, like feel free to just type them in chat or just ask me. So what I'm going to do is I'm going to go to this library. So GitHub. Sorry, I had a link on my Twitter. Here. So this library was developed by Jesse Vig. And this is sort of what the attention layers look like. So you can see here, they're saying the attention head visualizes the attention patterns produced by one or more attention heads given in a transformer layer. So CLS, for context, like this is just a new line separator. Like think of it as -n. It's just like a BERT-specific thing. And SEP is, think of it as a dot. Like it just separates sentences. Why is it not dot or -n? It totally could be. It's just that this is convention at this point. And so you'll notice this. Like, so let's say here the rabbit quickly hopped and then the turtle slowly crawled. And so let's say we want to come in here. And the point is like, let's say here we see a strong connection hopped. And then you see this really thick connection here. Like there's a bunch of arrows coming in, but it looks like the thickest one here is coming in from the word habit, which is like, if you think about like some stuff like embeddings, like basically so given two words, W1, W2, attention of W1, W2 is high if words are related. So what does this mean? Like in sort of the simplest case, like in some of the traditional NLP literature, like before deep learning, like this is just done based on counts. Like so the more a certain word occurs in a sentence, like let's say in a certain in a context around that word or in a sentence with that word, the more tightly those meanings are related. But attention is sort of like a generalization of this idea. Um, and so you'll notice here like, a few things. Like first off, they're saying, okay, well, this is the attention at layer 0, right? And so what's going to basically happen is that ideally we want different layers to specialize in different things. And we want the final layers to specialize and some of the lower level layers to learn some more domain specific stuff. So this is very common. Like, I mean, this is sort of a, like, if you look at, let's say, while this isn't necessarily common yet in NLP, or at least it became with transformers, if you look at a convolutional network, for example, typically you'll have, like, let's say, layer 0, 1, 2, do, for example, edge detection. And then, like, layer n will do object classification. Right? So these sort of tasks and images are inherently hierarchical, and the earlier layers in a network will learn these sort of higher level tasks, and then the later layers will learn some stuff that's a bit more high level or more domain specific. So this is very similar. So like this is showing layer 0, but then like sort of here. So what is this, right? So this is saying we want to see, like, let's say you have one model, and then this model has, let's say, 4 layers, and then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 attention heads. So we're going to have 4 by 12, visualizations of these networks. And the reason this is nice is because this sort of gives you like this high-level overview of what's going on. As in, like, this is sort of a summary. Like, instead of, let's say, sharing with a peer of yours like weights, you can share like an image like this, and this gives you a pretty good idea of what the network looks like. So for example, here you'll notice that different layers, like here, like at layer, like even though these look fairly different, you'll notice that at the second layer it seems to be putting a lot of emphasis from like the middle sentences all the way to the first one. Here it seems to be like, well, everything is connected to everything, which sort of makes sense in early layers because the network doesn't know enough for what to do. And then here in the end, it's sort of like it has these really strong connections to a couple of words. I mean, this could be anything, but I'm suspecting it's because the network sort of figured out which words are important for another word. So this is called the model view. But then there's also this other view called the Neuron View, which is, so basically in any sort of attention network, you have like a query and you have this key. Once you take the dot product of it, like this gives you a softmax to figure out like, well, what was the most likely word, like what's the most related word given this word. So why are we doing this, right? Like when you think of it, like let's say I'm saying I want to get the attention between word I and then word I dash, where word I dash is all words except WI, right? So we're gonna compute this attention over all words, and then we're gonna do a softmax, which is, as the name implies, basically a continuous version of the max function. And we're going to get the word WJ such that the attention, I'll write it this like WI of WJ greater than attention of WI W K for all K not equal to I or J. Look a bit more formal, but this sort of gives you an idea of what we mean here. And so this sort of gives us like an individual neuron view. So by neuron view here, like let's say when you come in here, like I forget if blue, I believe blue means highly related. Let's see. So the cat sat on. So cat sat. Yes. Let's see. So on sat. Okay, yeah, so it's saying like the most related words here, the most related word to on here is sat. That's why it's so thick and blue. We'll visualize this. So how does this work? So first off, it depends on the Transformers project. By the Transformers project, like this is Hugging Face's PyTorch project. So they've sort of integrated it nicely. Otherwise, like this also is dependent on Jupyter to show the visualization, on TQDM, which is just a way to visualize progress. IPython, also another Jupyter request, is a way to do HTTP calls. Regex, and then sentence piece. So sentence piece is basically a way to tokenize words by taking all the characters and all the words and just sort of, mushing everything together. But they also seem to have like a nice just requirements, like a requirements.txt for it. So it's potentially another thing you could leverage. So what we're gonna do is, like, I'm not actually gonna run this thing locally. Like, what I'm gonna be doing is I'm gonna be going through the notebooks. We're gonna look at the visualizations, and I'm also gonna look at the paper. And then I also want to actually just look at the source code and figure out, well, how do you actually integrate this into any sort of BERT library that you may have? Like, let's say you're not actually using Hugging Face, like you have your own transformer. Well, like, how could you reasonably hook this up? Okay, so let's get started. So first off, like, if you go to the paper, it's saying, okay, it's a multi-scale visualization of attention in the transformer model, and they introduced the model view, the encoder view. So let's just look at like a few more examples here, because I think the examples in the paper are a lot better than the examples in the GitHub. So for example, here you'll see like attention heads for GPT-3 for the quick brown fox. The left and center represents different layers attention head, and the right figure depicts the same layer head as the center figure, but with the token lazy selected. Right? Okay. So let's say here, if you put, okay, interesting. So first off, like they're showing like the most, like the strongest connection here in layer 4 is basically the previous word. Like what this is doing is this attention head is paying attention to the previous word in a sentence, and only in the case of it only pays attention to itself since there's nothing before it. So similarly here for the. But then if you come in and let's say hover over lazy, it's sort of paying attention to everything except the. Maybe it's not a very important word. But anyway, if we keep going, like here, for example, the cat sat lay on the rug. The cat sat on the mat and the cat lay on the rug. Is there still attention here? Yeah. So far, I think these examples, like with these visualizations, aren't particularly interesting. And I think they actually become a lot more obvious once you look at proteins. So I'll be sure to show you an example of that next. But yeah, let's see. So examples of attention heads in GPT-2 that capture specific lexical patterns. So list item, left, verbs, center, and acronyms. And similar patterns were observed in attention heads for other inputs. Right here. So for example, let's say in layer 8, at the store, she bought apples. Okay. This is everything. The dog ran up to the street and barked loudly. List item, verbs, center, acronyms. I mean, yeah, like this is interesting. So one thing, like just sort of some context that will make this point more obvious. So traditionally in the NLP literature, we have like these sort of like similarly how in vision you had like these hard-coded extractors. In language, like let's say Mark, let's go back to the example of Mark is hungry. So for example, this is a proper noun, right? And then hungry is an adjective. And then I forget what this is. Some like an article or whatever, a connective or whatever. So this is called the part of speech tags. But then there's also something called the dependency parse. So if you like look at the dependency parse right here, this will look something like this. So someone like the object of this, it'll look something like this. So basically, like who is hungry? Like who is hungry, and the answer. So this is the question, and then the answer is Mark. So the nice thing, like the reason I make this point is that ideally, instead of you having like a rules-based model for this stuff, which is stuff I worked on before, and I can tell you from experience is a huge pain in the ass, like why not learn the most important tags for your word via attention heads? And so the next double point is, if your attention heads have similar patterns to what you would expect from a rule-based model that implements part-of-speech tags or dependency parses, then you can sort of with confidence say my attention model is learning something interesting. But there's a bunch of side effects to this as well. Like let's say if you're trying to visualize like whether your model is very sparse or it's very dense, you could also look at the attention layers and figure that out just by visual inspection. So back to the paper. So for example, here like they notice that some layers are related to occupation, some layers are related to your name, and some layers are related to your gender. So the point here is that there's like NLP has like I don't know, like so many possible like data like featurizers, and can you skip all of them with a large enough language model? So this point is sort of controversial because people are like, oh, like how dare I say that like a dumb network that's huge like outperforms stuff that has a lot more insight around it and a lot more study. Like I have a very simple opinion here. Like if something is works and is simple, then the dumb thing is actually the complicated thing. So I think until the perf gets better on these more complicated techniques, I don't think that's a very intellectual thing to say. So I think yes, like I mean, instead of it sucks building these rule-based models. They take a lot of domain expertise. They're fiddly. You have to debug them. And when you think of it, like actually there was this interesting talk by Tesla that talked about this. Like let's say you have a model for dependency parsing, you have a model for part-of-speech tagging, you have a model for co-references, and so each of these is a specific model, and then you feed these to a giant neural network, and then you solve a specific task. Like why not just like skip all of this? Like why not just immediately solve the problem that you're interested in solving instead of solving related problems that are actually not that interesting? The doctor asked, I'm not sure what you're talking about. The doctor asked the question. He asked her if she ever had a heart attack. Okay, interesting. So for example, this is like another way to measure bias, because like let's say if you notice that there's this more attention being directed from he to the word doctor than she to the word doctor, like just replace the sentences. Like this is just like an easy way to measure the bias. It doesn't mean that there's an easy way to fix it. It just means that you can detect it and using this mechanism. So ultimately, like the model is gonna look something like here. Yeah. So as you can see here, you're gonna have like these multiple attention heads. Why not just have one attention head? I don't know. Like it just seems to be a general trend in machine learning that like having like model aggregate. Sorry, like I'm just gonna pen. Like in general, I would say model aggregation good. Seems to be the overall piece of feedback here. But as you can see, like for example here, like this is showing like birth, and it's saying it's excluding a bunch of layers. But otherwise, like this sort of gives you like a sort of a mile high view of what this looks like. So this is the model view, but there's also a neuron view, which you can use to come in and say, okay, well, like let's say, so you come in here and you're like, okay, and you can see, for example, here, like let's say they're showing, this is not a very interesting word in particulars. Let's keep going. Oh, that's it, we're done. Okay, so let's say here, like they'll say something like the soft, like, okay, so the dot, okay, that's not very interesting. I think what we need to do is just like look at the visualization ourselves and play around with it and see what makes sense. So let's open Roberta. Oh no, there's no collab. Let's open Bert, and then let's open Bert again. First, I'll look at Bert. Okay, excellent. So let's look at some of these sentences. So first off, can I modify this? See what happens if I do this. Okay, I think it's just running it on my machine. Okay, I should have done this earlier, but it's okay. Let's I guess we can use this time, while it runs, we can use this time to figure out how all of this stuff works. But basically at a high level, what's going on is we're just cloning the repo. We're creating, we're calling HTML. Okay, what is this doing? So we're importing IPython, and then we're saying, okay, make sure that required.js is installed, make sure that you have D3 and jQuery. And then how is this actually used? So we say we have a model type, model version, and then we get the pre-trained model from the Hugging Face library. We get the tokenizer from Hugging Face as well. We just make a call to this HTML thing, and then we say we want to show the model type, tokenizer, sentence A. So how does excuse me. So I mean, I am a bit confused. Oh yeah, so it's here. So Bert. So this is sort of the code I think we want to look at. Bert Viz transformers neuron view. So I think this is going to be the code that we look at. So let me just copy paste this in. And this will give us an idea of how all of this works. It looks like this is finished running, so that's excellent. So let's just run this and see how it works. Thank you, Habibi. Sorry, my throat starts hurting usually in the middle of these streams, so I got this tea that a bunch of singers recommended to me on Twitter. It's pretty good. It tastes awful, but it does make my throat feel better. All right, so let's see. So let's just write down a to-do list for ourselves, right? So we're going to come in and we're going to say, well, the Bert Viz transformers, Neuron View, it's also importing Bert model and Bert tokenizer from Bert Viz. And then it's showing it here. So first off, is this running? I mean, I want to change the sentences a bit. The cat lay on the mat, the cat lay on the rug. So I want to change this to something like she is a great doctor, and then I want to make this he is a great doctor. And let's see if this works. So it's taking a while because this is, I believe, downloading the entire BERT pre-trained model. I would expect it's downloading a smaller version of it. So in this case, it's downloading a BERT base uncased. Oh, this is not a small model, actually. So I don't know how long this is going to take. Oh, looks like it's done. Let's see. It's promising. It's going to zoom in a bit. All right, great. So you can see here, for example, okay, so are we seeing the bias thing, for example, here? So if I look at the doctor here, when it goes to he, it looks, actually, yeah, so here. Oh, okay. So here, for example, the two strongest connections are between she and is, and then for he, I mean, correct me if I'm wrong, everyone, it looks to me like if there is a difference, it's small, I guess. So I don't know, maybe they fix this. But like I said here, so let's say, so here they're saying, okay, we want all attention. But like, let's say this was layer 0, layer 0, and then head 0. So let's instead try, for example, layer 1 and look at the difference. So in layer 1, for example, we'll see that like A is, let's see. So so this is related to great, and then this is related to separator. Okay, separator is related. Okay, so this is interesting. So the separator sentence has the strongest attention to the beginning of a sentence. So I guess it's sort of communicating where does the sentence begin and end. Great. Okay, so this particular layer seems to be paying attention to line separators, right? So let's keep going. So then, okay, so here it's focusing on something really concrete. So it seems like it's focusing on the next word in a sentence. Yeah. This is pretty cool. So let's say if we go to 3 now. Okay, so this is saying like is and then great. So here, for example, layer 3 seems to be mostly about figuring out attention to a word from itself. This is an attention layer paying the most attention to line separators. Okay, I didn't expect this to be so like it really feels like each one has a specific feature. Let's see, layer 6. Oh, interesting. So this is giving us the neuron view. Okay, I mean, let's take a look at this. So I'm going to go to the final layer. I don't want to look at layer 0 anymore. Like, it's interesting to me how like the separator seems to be the most important part for all of these attentions. Okay. This looks a bit... Oh, this is the one paying attention to itself, I believe. Yes, it is. Let's go a bit up. Okay, so example, this is paying attention to the word before. But notice like none of this was programmed. Okay, this is a bit messier. Let's take a look at this. So I just see like this is mainly paying attention to the sentence boundaries at the end of a sentence. Similarly here. Let's take a look at this. Layer 7. Okay, so layer 7 was the word before, if I'm not mistaken. Okay, I wonder if there's just a way to visualize it for all layers and all heads at once. I guess we'll get to that. Oh, it's this one, I guess. Okay, so let me just run this in the meantime. But let's just take a quick look at the code. So far it looks identical. And the only thing that's showing is, as opposed to saying show, we're looking at model view here. So this tells us like this is the second piece of code we want to look at. Right? So this gives us a sort of roadmap for what we're actually trying to understand for today. Let's put this here. And let's see. So same thing. So we get a model. We use one of the built-in BERT tokenizers. Okay, we use some input IDs. We get the attentions. We call HTML, and then the model view takes in attention and tokens. So in this case, how are the tokens generated? So let's take a look. So if we look at the tokens. So tokenizer convert IDs to tokens, and then this takes in the input ID list. Input ID list takes input IDs, which is inputs, IDs. Inputs is tokenizer encode sentence A, sentence B, return tensors, and add special tokens true. All right, and then so this is all Hugging Face stuff. Like none of this is by this author. So then we have these IDs, and then okay. So once we're feeding this in attention and tokens, I think one thing I'm curious about, and it would have been useful to run this through a debugger, is to actually see what the attention's data structure actually looks like. So I'll let this download. Like I think this should be downloading directly on Google servers, so that's why it's way faster than my connections. All right, excellent. So I created the models view. So what I want to do now is, I mean, let's just see what this looks like for like a different kind of. I mean, I'm literally maybe super hacky. Put this and dump this here, and then let's say I want to put in our example from before. So he is a great doctor, and then sentence B will be she is a great doctor. This may be a bit hard to compare. So I'm just going to actually save the image. So maybe I'll take a screenshot. So let's do this. Zoom out. This is pretty big, but it's okay. I think like we can just sort of get a visual idea for what this may look like. And then I'm going to come in here. Let's say I dump this here. Right? Then same thing for the thing below it. So I'm just curious in general, like do these things look fairly similar for different sentences? Because I definitely would not expect that to be the case. Okay, let's take a look. So I think the first thing that sort of I find striking here is that they actually do look fairly similar, which is sort of surprising to me. I don't know why because I think I may have zoomed in and out. But like, I mean, like, look at this, right? Like this sort of looks like this sort of looks like this. The pink here has these sort of similar patterns. And so I think like, are the sentences the same length? Is that maybe the issue? So the cat sat on the mat. Okay, 5. And then, yes, I still count on my fingers. And then he is a great doctor. He is a damn. Let's try this. It's just crazy how similar they still look. And it could be because the sentences have similar. So the cat sat on the mat. No, they don't have similar grammatical structures at all, actually, because one is about like you're making an action, then the other one is a description. So I wouldn't, a priori expect these to be similar, but they are, which is interesting. So yeah, so I think open question for me is, uh, so given two different sentences, attention maps look fairly alike. So I'll just put this as a sort of open question for me. Like, why is that really the case? But this is cool, right? So, and like just to be clear here, so going back here, there's the code. So just the way this is called, so model view uses okay, so this is for the model view, and then the neuron view. Okay, yeah, the neuron view is a bit longer. It also takes in the sentences. Let's open this up. Yeah, so I'm just gonna call this, like, this is the usage. And so now I think like the next piece of this puzzle is sort of figuring out, okay, great, like let's say we do have something like birth implemented. How do we use this? And so let's say, so here it's saying, okay, well, we have a birth tokenizer from pre-trained with a model version, and then do lowercase, and then sentence, yeah, so here. So for some reason here, show also takes in the tokenizer. So it's interesting to me because here it seems like, I don't know, like a lot of this stuff could have been done in models and here instead. But yeah, like model view takes in attention and tokens, and then show takes in the actual model, the model type, and the tokenizer and the sentence. Yeah, so I think like the APIs were sort of built with two different levels of granularity. So maybe I'll write that for myself. So the APIs have different levels of granularity. Right, excellent. Oh, yeah. So like the way my tablet works is it's actually a mouse. So when I lay on it, it ends up giving me this like weird stuttery behavior. All right, and so one thing I'm also curious about is here. Oh yeah, like these look like they were built at different times, right? Like check this out. Like here in transformers, they're importing the birth tokenizer and then the birth model, whereas here he's using his own model and tokenizer. So if this is to be used like a library, this needs to be fixed. Okay, yeah. So let's say, so show uses a custom transformer, and then model view uses the Hugging Face. All right, so this is all good. And oh, I see. Okay, yeah, so this is sort of a state issue. Kind of like this idea of just like sticking stuff to the whiteboard. Good job, Microsoft. But in all cases, um, I think we're in good shape right now. So a lot of this here is like, let's say, visualizing specific models. I mean, let's say if I look at Albert, is it very different? Okay, there's this config. Show head view. From pre-trained model. Yeah, it's just like it's not super general, I guess, here. Let's say let's head view BERT. Show head view, attention, sentence B, input to list. And then, okay, it's an IPython core display. Okay, again, makes sense. So if I'm not mistaken, yeah, so this is like, there's a lot of them. And then the images here are, I believe, for the README. So if we go here to BERT, and I think, actually, so first off, so where was the code supposed to be? So from BERT_viz.neuron, yeah, so we want .neuron, a model view. Okay, so the code we want to look at is BERT_viz. So actually, to get maybe like a sense of usually how complicated a certain library is, like one trick like I learned from a friend is I go to dev and then I go to, in this case, it's BERT_viz, and then I type clock and then dash dot, and then this gives me a total line of codes divided by type of file. So this gives me like a good high-level view of the complexity of a project. So here I can see, well, okay, well, this is about 7,000 lines of Python, it's about 9 lines of Markdown, 10 lines of JSON, and about 1,500 lines of JavaScript, which is, I'm assuming, where most of the visualization is happening. So it's not like it's not like insane, but it's not a toy project either. Like I can tell that there's been a lot of thoughts put into this. Actually, one thing I'm curious about, like what are people complaining about here? Could you let me know how to use BERT_viz for name entity recognition? On chaining. Let's see. I'm trying to get the basic BERT visualization using Chrome on my local machine. The notebook throwing an error when I execute the shell. Returns an error. JavaScript error required is not defined. I tried doing a clean pip install from your requirements. Alright, everything else found for Jupyter is a specific Jupyter required package, and also used any idea what's going on here. I tried opening a notebook, very slow environment, and it worked fine, so it's all reasonable work on for me. If there's any feedback, I'd love to hear it. Otherwise, feel free to just close it. Thank you. Yeah, okay, I'm not going to answer this. Yeah, so let's see here in head view. So okay, like let's look at the files we want to take a look at. So there's head view, there's model view. Okay, yeah, it's actually all of them, and then utils, and then what's transformers, neuron view, modeling BERT. Let's take a look at this. modeling utils, tokenization BERT. All right, okay. All right, so let's go here. Get rid of this, get rid of this. Here we're good. So, interesting here. So this looks like, yeah, this is not his code. That's what I figured too. So I think he probably just added the libraries here, so that he doesn't have to like import them or anything like that, or maybe he just needed this part. So it makes sense why you just have the tokenizer here. Something for Chinese, for word piece, probably sentence piece at some point. Okay, great. Modeling utils. So again, this is made by Hugging Face. What is this about? Pre-trained config. Okay, so if I'm not mistaken, this just looks like a way to import models. One deconvolution, pooling, okay, sure. We don't need this. Okay, modeling BERT. This, okay, again, looks like Hugging Face code. So load TensorFlow weights in BERT. Okay, there's an activation function, the famous swish activation function. Okay, so this is BERT with this pre-trained config, the number, okay, yeah, so for example, you can see here that there's like 12 hidden layers, 12 attention heads, is the intermediate size, this is the dropout probability, this is the type of the vocab. There's the embeddings, BERT self-attention. Oh yeah, so this is the query key values that like they talk about. So you'll see here that it's just basically like a linear. It's like a dot product between the hidden size and then the head size. You do this 3 times, but because there are 3 different parameters, they're going to learn different things. Yeah, so then here, this is kind of nice actually, because I'd read other implementations a couple of weeks back, but I think I can understand Hugging Face implementation pretty well at this point. I think that's the benefit of doing the same thing over and over again. But anyway, like, let's see here. Let's go up. Okay, so I don't think this is what I need either. Actually, is there here attention? Is it? So format attention. That does not have the correct number of dimensions. Squeezed. Format special characters. Replace G by nothing. This by nothing. Lily by nothing. 14 tokens. And torch.stack squeezed. And then it was squeezed. So squeezed has all the layers. If layer.attention.shape not equal to 4, because it's number of heads, sequence length. Oh, interesting. Output attention's true when initializing your model. Okay, this is interesting. So let's see. I'm just gonna copy paste this over here. Yeah, so basically, so model needs to output attention. All right, so we can keep going. So here I'm at the neuron view.py. Yeah, I like this. Like, I mean, because I haven't done web dev stuff or these nice visualizations in Python, so I'm actually pretty curious how they make this work. I guess before we go to the neuron view, maybe I can check out the model view or the head view, because that makes more intuitive sense to me so far. I don't entirely get how the neuron view works, actually. So you can get rid of this. Model view shows black image. Import model view attention tokens. Okay, so one thing I want to make sure of here is when they say tokens, because here, for example, it's just being fed the actual tokenizer. I just want to give it the tokens, though. Whereas here, it's being fed the tokens. I guess I could always start working with the model view first. So the tokens seem to be... Yeah, so is this running, actually? So it's... Okay, and then what about the attentions? Okay, this is great. So this is what I need. So I'm gonna take a screenshot. I'm gonna make this delay like 2 seconds. Alright, so then this is what the attention needs to look like. And then let's look at the token. Let's do the same thing for tokens. I'm just gonna click this. And then... Yeah, so the tokens are actually here, in this case, the sentences. And then the attention is like a 4-dimensional matrix that starts with 1, then has the number of attention heads. And then it has this thing 15 by 15. So why is it 15? So it's 1, 2, 3, 5, and then 5 words. So it should be 10. What do I hear? Okay, so how's the attention computed? So, okay, yeah, so in this case, so it's in BERT model, and then the first, it's the last, okay, yeah. Okay, so this is what I need. So, sorry, let's take a screenshot, it'll be better. And remove the delay, and then this is how you get the attentions. And then tokens are really trivial to get. Like, it's just you would call the tokenizer on a sentence, and it would give you these lists of tokens. Why is this so tiny? Become bigger. Okay, excellent. Okay, so I'm just gonna write this, and then tokens, trivial, to obtain, and then attention is we look at the last output of BERT model. All right, so we're getting close. I mean, like we're pretty close to figuring out how to make this work in a custom way. I guess the next step will be like going into BirdViz, still actually doing the deep dive. I think it took us about an hour to figure out how it works, why it works. But yeah, let's do that next. So if I go to the, I think I'm gonna go to birth model. Where is it? Birth model. All right. So birth model here, and then if I say, I mean, does this return anything? Return base model output with pooling. So in this case, when we're calling the actual model, so birth model, okay, so from pre-trained, then we're giving it the input IDs, and we're giving it a bunch of tokens. Birth model. Pre-trained. All right, so it looks like in this case it returned. I mean, I'm pretty sure it looks like it returns this thing because this is not inside of a function. Oh, it is actually. It's the forward layer. Let me just make sure. Yeah, so this is returned here. Okay, right. So if then we're giving this thing, where is it? So we're giving it a model version. Birth token. Oh, this is still the tokenizer, actually. Sorry. So model, and then yeah, birth model, which inherits from pre-trained model. Sure. It takes in the input IDs, which is a tensor of shape 1 to 15. Oh, actually, so we have 5 words, and then we have 2 beginning sentence, and then 2 end sentence. Oh, I see. That's where the 15 is coming from, because we're adding the separators. Okay, yeah, this makes sense. And then what's token type? Token type IDs. So just, I guess, some IDs for it. So I think what I want to do here is I want to basically say, let's say we have this. I just want to like inspect the model data structure, at least what it looks like. Why did it? Okay. So then I'm going to create a new code fragment, and then I'm going to say model. Okay, I wish I could read this. Let's see, so model, let's see, if I say model 0, what happens? So it's a tensor. Okay, what happens if I show model 1? Okay, so it's the forward tensor, the backward activations. And then this is immediately out of range, but if I go model -1, Okay, so this is saying the softmax backward. So I believe it's just taking the second. It's just taking the backward pass, it looks like. If I'm not mistaken, yes. Okay, so now that we know that, let's see. Does it say anywhere? So this is an embedding. It takes an encoder and it takes a pooler. Then it initializes the weights. Actually, I know what to do. So let's say if I say model dot config. Nope. Let's say model dot embeddings. Also nope. And then embeddings, word embeddings. So what is model actually returning here? Like, is this should be an object? Because okay, this is all in the forward pass, which is nice and all, but that's not actually what we want to be returning. So I can maybe I can see the type of find class type of object Python. Okay, so let's see type of model. It's a tuple. It's a tuple. Okay, so let me just put this as a sort of TBD for later. I think it'll make more sense once we get to the actual work. This is a bit confusing. We'll figure it out. Okay, so I'll come in here and I'll say model is a tuple. So with tensor for the forward and backward pass. All right, so great. So now let's assume that, so we already said that the attention is sort of this four-dimensional matrix where you have 1 times the number of heads times the number of tokens times the number of tokens again, right? So I'll just actually write that because I thought it was a good point. So attention size is 1 times number of heads times number of tokens times number of tokens. Actually, so before I forget, I did want to show you guys one interesting thing. So if we go to the protein paper, I think it was here. No, not Procgen. It was in this folder. And then, yeah, it was in this Bertology paper. I was planning on making like a longer video about this, like something more edited. But this is sort of what I thought was really interesting, where attention to amino acid probe. So yeah, so you'll notice here that there's some specific. I mean, I think this is a bit of a different visualization. So I may need to implement some of this stuff from scratch, but I'll put it here. So then I'll write myself, like, okay, so you'll notice here that, for example, like in amino acids, what's sort of unique about them is that it's a much smaller vocabulary than English. Like you have like what, about like 20 amino acids. So here we can see that at layer 1 and then head number 11, we pay a lot of attention to the amino acid probe. And the point here is that, like in, let's say, in proteins, the vocab is small, so you can take a layer average across the entire data set. So as opposed to looking at a specific sequences, you can look at all sequences. All right, so, but back to this work here. So I think I'm gonna look at maybe the model view and the head view, and then we could potentially do the neuron view some other time. I'm just gonna remove this, and get rid of this, get rid of this, get rid of this, and get rid of this. Great. So first thing I'm curious about is, let's look at the JavaScript for this. So when we come in, okay, it requires D3 and JS. It has some detail around like the sizes of the boxes. It sets some global state variables like the number of layers, the number of heads, which is set up from the config. And this config is obtained from where exactly? Okay, looks like we're going to pass this in as a parameter. And then it has a thumbnail height and a width. Sure, and then we're going to render the thumbnail. How do you render the thumbnail? Define line 65. Head index, thumbnail index, and then render detail. Sure. Okay, so we're basically just going to start drawing like each of these heads, and then when it comes to render detail, okay, we're just setting up the padding, like the width, the frame, and the detailed heading, and then this is kind of cool actually. I didn't know SVG in JavaScript was so nice. Like you just like say, okay, I want this attribute, then this attribute. I think it's like probably does it like they do it via callbacks, like because it just returns the function itself. So it's cool about functional languages actually. Instead of stupid return statements. But yeah, like it uses so config.svg.depend. So where is svg first defined here? Config. Okay. On highlight selection, render thumbnail attention, attention container. Okay, click region, mouse over, D3 select this, style pointer. On shit, okay. So the main point here, I think, like the sort of high level way this works. No, that's not what I want. I didn't want to render, so thank you, GitHub. That was unnecessary. But yeah, I would say the main idea here is that we pass in a config object with attention and tokens, and we set up the attention neuron, sorry, the model visualization here. So let's see, so if we keep going, then we have this attribute. Just a moment, let me put the battery on for chat. So config on highlight selection, sure, and it uses the thumbnail width, thumbnail padding. I guess this is why I like Unity, because like I feel like I can make any sort of complex UI that I want. Like when I look at this, I'm just like, I don't want to go back to JavaScript world. Like I really disliked it. My brief experience with web development. Look region, rectangle. Okay, but anyway, we can look at the Python. So attention, it's a list of torch float tensors, one of each layer of shape. Batch size must be 1, number of heads, sequence length, and then sequence length. And then index of first word piece and sentence. If input text is a sentence pair. And then it indicates whether to remove special characters and word pieces. Okay. So if sentence B start is none, then span style, these are select none. Option all A. Okay, so these are all the options in the menu. Otherwise, just show no options. Just show it. Then it displaying it, OS real path, and then the directory name, OS join model Vue.js. Okay, so open the JavaScript file. All right. And then it's saying format attention. Okay. So I think this was very telling here. So the model view, at least here, so attention heads should be torch dot float tensors. All right. So okay. So I mean, first off, let me look at where attention is. So he comes in, and then you have this thing called attention, and then attention data is setting up this nice like JSON object. I didn't know that Python. Oh no, this is the dictionary though. I see. This is kind of cool actually. I didn't know that you could make this so easy for web stuff too. Like just work with these kind of dictionaries. Attention data. Display JavaScript Windows parameters. JSON dumps parameters. Okay, so let's just take a look at format attention again. So format attention. So then we say for attention, for layer attention and attention. Okay, so it gets passed in a list of attentions. As a torch stack. Yeah, so let's keep this as well. right? And then if we go back, then attention, they basically do this to visualize it. And so now the question is, how do you get it in this attention format if it wasn't a PyTorch tensor? Let's say this was in TensorFlow, for example. How do you make this work? So, okay, so I think that is explained if we, again, I think go back to the original Colab file, BERT. And you'll see here, for example, the attention is taken as the last layer from here. All right, and then, yeah, so what we need to do is, and I think, by the way, this is it, guys. I think I'm going to call it after this. So I'm just going to write this here. So basically, summary, get attention heads as a tensor of size 1 times number of heads times number of tokens times number of tokens. And I think that's gonna be it, guys. Like, I hope you enjoyed this. Like, so as a sort of summary, what we talked about, I think, today, and again, feel free to ask me any questions about any of the above. So we talked about like attention and transformer models for NLP and proteins. We also talked about basically how to measure attention quality, right? Then we talked about this visualizing the heads with the neuron view, the model view, and head view. We looked at examples on Colab, and then we looked at how to implement, basically how to hook up to BERTviz. And then we also studied the source code with the JavaScript config and populating an SVG visualization in D3 from Python. So that's a lot more than I expected to cover, but I hope you enjoyed it. And if you did, feel free to subscribe and come into the next one. Thank you so much, everyone. I appreciate it.